Get started here. The Contaminated Sediment Transport Module in EFDC, or the Toxics Transport Module, depending on how you look at it, is designed to work essentially solely in conjunction with the sediment transport module. You can't do any toxics transport if it was just dissolved phase toxics right now in EFDC. You'd have to have some kind of inorganic sediment component configured to run right now, because pretty much the rationale is that all of these persistent organic pollutants and metals, contaminants are all basically particle active. They all, at some level, like to attach to sediment particle through organic carbon that's on the particle or in the water itself, attaching to that and then migrating. That's the reason why you pretty much have to have sediment working, sediment transport model working before you can turn on the toxics model. And EE prevents you from turning on the toxics model right now unless you first have the sediment transport module turned on. So when we're talking about toxics transport in EFDC, anybody, not just us, it'll be always associated with a contaminated sediment issue. These are just a couple of examples that I found. Actually, this one was on the internet, but Earl, that one should be pretty familiar to us. That's the Housatonic River, the half-mile cleanup right outside Pittsfield. But they had, GE had a significant release over the years for PCBs and other organics, and contaminated a long stretch of river. And anyways, this is their cleanup. They put in sheet pile, and they're coming in and digging out all the contaminated sediment and moving it elsewhere. I don't know what that thing costs. Do you have any idea what that ultimately? But I mean, they're typically, these contaminated sediment sites, when they're in rivers and in a major water body, your figures are in billions of dollars. It's just a huge amount of money to deal with these sites, but they're not always that bad. I mean, this one up here, this is a Coast Guard cleanup site where they had contaminated sediment that they're remediating. That's actually a little cell that they're putting some of the contaminated sediment into after removal. But it's these chemicals, these organics. They attach themselves to sediments, and so pretty much where the sediments go, a lot of times, that's where your contaminants are. So if you've got an area downstream in a riverine system, and it's downstream of your toxic waste site, and you've got erosion that may have been occurring over the years, if you've got an eddy somewhere downstream, likely that's going to be a hot spot for contaminants, because that's where the material will have accumulated from anything that may have eroded off of the site. So, you pretty much have to do everything, coupled. Sediment transport, make sure that that's right, reasonably accurate as you can get, and then add on toxics. There's just this probably a good point to make here at this stage. If you want to simulate toxics, that's your end game in developing a model. And let's say you've got it's a salinity and maybe even a temperature dependent system with that you need to address. I think you probably covered this in the intro section, but you don't want to build the most complex model for the very first time you build the model. We recommend that you build on essentially a series of building blocks. You start simple, hydrodynamics only, nothing else turned on, kind of get that working. Then you add your density dependent components and start going multi-layer if you need to go multi-layer. Then you add on toxics or sediments, get sediments kind of nailed down. Then you move to the toxics, because every time you add one of these constituents, it adds computational time, data needs, and so it's really very helpful if you do it in a logical progression, using that process. And it's kind of, we have some general modeling guidelines that are on the website to kind of help you guide you through that path, or at least just remind you what it is. So what we're going to cover this morning is just a kind of a quick intro to contaminants. Very, very quick. I didn't have as much time as I'd like to kind of prepare everything, but so this will be a lot more ad hoc than yesterday, and that was pretty ad hoc. So then we're going to cover partitioning contaminants to organics in the water column and the sediment bed. Then we'll jump into the EFTC theory, look at some of the EFTC specific, toxic specific files, and then again just show you that documentation link, which works for you guys but didn't work for me. So let's just kind of look at, so just a quick reminder, what is a hydrocarbon? It's a carbon-hydrogen, molecule. You've got different groups of hydrocarbons, aliphatics, which are your single chain, of which you have, single bonded and double bonded, and I'm not exactly sure what an alkyne is, but it's obviously a more complex bind. And then you've got basically your rings, but this is a single bond ring somehow, but this is your aromatics, and aromatics are that's where you have the double bonded hex 6 carbon ring, and then you got all kinds of variations of that, and that makes a host of different compounds, which we'll look at. So generally, when you're talking about organic contaminants that we're dealing with, we're generally mostly looking at aromatics because, well, they break down much slower. This is a chart here looking at organics, kind of on the outside, their names and kind of a general symbol of that particular compound, and then kind of looking at it from the standpoint of vapor pressure, things that are that are highly volatile, and this is decreasing scale, and then it kind of loops back over and continues the scale over here. So and then as you note here from the schematic, what you're looking at is very simple compounds, and then as you get more complex, you get into the aromatics, where you start having your carbon rings, and then they start binding together, and you start adding chlorines and other materials to it, but most of the time it's chlorines that cause the biggest problem. But as you make these compounds more and more complex, they become bigger and bigger, they become less volatile, they become less bioavailable for degradation, and to the point where you get down to what we like to call persistent organic pollutants. These things have very long half-lives sometimes. I mean, they can be in the thousands of years for some of these materials here. And these are some of the bad actors, but there's a lot of other bad actors. These are just a short list of some of them. So, it's if something, go back up here, like if you've got a benzene here, for instance, benzene has a density, it's lighter than water, so it's a L-NAPL, a light non-aqueous phase liquid, and it will, if it gets into the water column, it'll tend to float. So you have volatilization working for you, so it goes away pretty quick. And then what doesn't go away if it's in an organic, an oxygen and, rich environment, it biodegrades relatively easily. So benzene's not really a particular problem. Acetone, toluene, a little bit more, a little less volatile, a little harder to degrade. But you know, these chemicals over here are pretty much not an issue for most toxic contaminant sites. Now, if you've got an acute spill, you've got a big gas tank and it ruptures, and you know, but that's kind of a different kind of beast. And you may have to model that scenario if it's a significant issue, but it's generally not what we, you know, that's a concern at these legacy sites that are, you know, from historic contamination, which is usually what we're dealing with. So, I mean, that's, as I said, it's pretty quick overview of what I mean by toxics and toxic contamination. I didn't even talk about metals, but obviously metals are also of a concern, and they also sorb to sediments. One of the what do I want to say, unique characteristics of metals is that they're subject to pH and redox conditions in the water and in the sediment bed. And right now, EFTC plus doesn't account for redox conditions in any of the partitioning and transport processes. And that's why I was saying that's what 8.4, we want to bring in pH as an option, so that then it can start having its influence on reaction rates and partitioning and metal speciation. So that's something that will be down the road. But I mean, historically, EFTC has been used for inorganic toxic transport as well as organic toxic transport. And you know, you just end up with kind of a bulk behavior of the material, and a lot of times that's plenty good enough. So let's just talk a little bit about partitioning. Now, partitioning fundamentally is how much of the material, of the total amount of mass of a contaminant, how much of it is attached to the sediment and how much of it is dissolved in the water column. And there are different kinds of partitioning, equilibrium partitioning, which is the approach that EFTC uses. There is a more kinetic process where it allows time to reach steady state or equilibrium, but EFTC assumes instantaneous equilibrium partitioning. And that's a very common, again, approach, but that is what EFTC right now is doing. So, you know, just different types of equilibrium partitioning, but the one that we're focusing on here is the solution to a solid, adsorption partitioning. And generally, the units of your partitioning coefficient, in your concentration, are in milligrams per liter, and your partition, now that's the solids, milligrams per kilogram for the solids. I'll get to the partition coefficient units later. But you know, what we're looking at here is, you know, every species has to have its own partition coefficient, and oftentimes it is going to be a function of the amount of organic carbon that's available in your material. If organic carbon is not a particular concern, you can use what's referred to as just a distribution ratio, or a KD approach. And that is literally strictly just the KD is equal to the amount of material in the water divided by the total amount of material in a unit volume. So this is the simplest approach, and EFTC has that ability, and we'll look at that later. And it's basically what it's doing is it's just lumping all the detailed processes and saying, yeah, we know that there's a lot of maybe, you know, variability and you know, details around maybe a very complex process, but we don't really have the data to parameterize it. And that's really not a big concern, so they lump it up into this distribution coefficient, or a KD. So just a few kind of basic definitions. What you're looking at here, this is total concentration in a unit volume. Then you've got your dissolved phase and your solid phase. They obviously have to equal one another. And then you've got your fraction of dissolved and your fraction of solid here. And then you have your distribution coefficient here. So your denominator is the total mass, which is that's again equal to your concentration here. So this one represents the mass in the water column, or dissolved rather, and this is the mass on the solids. So again, everything has to add up to unity, and all of these KDs here are all in units of cubic meters per gram or liters per milligram. So that product has is dimensionless. But this is the KD where we're ignoring organic carbon. Oftentimes, organic carbon is of significance, and I should have changed this to KD, but your partition coefficient is actually, or your KD is actually a product of your fraction of organic carbon on the specific size class that you're dealing with, times a KOC value, which is organic carbon specific distribution coefficient, so that it basically normalizes how much organic carbon is on your sediments. You can enter this one value here into the model, and it'll multiply it times the spatially and possibly temporally varying organic carbon that's in the system to vary your actual effective distribution coefficient for the calculations in the model. So this is a more standard approach to do the modeling. And then a lot of times in literature, your octanol water coefficient is reported instead of a KOC. And there's just a relationship of KOW to KOC using that conversion factor. So you can just go straight from KOW to your partition coefficient using this approach here. You would do this, you would actually take the KOW and multiply it times this, and that would be actually what would go into EFTC. But just so you can see how it works here.